All right, can you see my screen? Okay. First question is about constructing a function based on some properties where fx is defined for all real x. The first derivative of f exists and is negative for all x not equal to 0. The point x equals 0 is the local maximum of f. Okay, can you think of a function? If you want to talk, you can unmute and then share your thoughts. Fx equals 3x cubed plus 2x plus 5. Okay, let's plot that. Okay, someone gave me this answer. Let's plot it. Okay, that doesn't look correct. You can try plotting the function and give me that. Okay. If dash x exists and is negative and not equal to 0. Anyone? This could be a quiz question or an exam question, so you should be able to do this. I mean, this is a typical question. These are typical questions that could be asked. Can anyone else try? Just give your thoughts. It doesn't have to be correct. Maybe altogether you can find out the solution. Zhao made an attempt, but that's also good. start with something. Minus x squared, triplet, thanks. Is it on the entire real line? Let me put minus x squared. Does it satisfy the condition? Does this satisfy the condition, triplet? The derivative exists and is negative for all x not equal to 0. So, but in this case, the derivative is positive, right, on the left side. So, yeah. So that doesn't satisfy the condition. So thanks, so 1 over x cubed. And does that satisfy the point x equals 0 is the local maximum? So, yes or no? Or did you say yes, it does satisfy the third condition? Okay, okay, good try. I'm sure you can come up with something. Okay, I'll give a hint. Can you think of piecewise functions? Are you familiar with piecewise functions? Piecewise continuous functions? There should be a jump discontinuity in this case. Okay? Maybe there is a graph which is decreasing on the left. So, and then up to 0. And then from 0 onwards, maybe it starts up there and then again decreases. Okay, let me share something which we can refer to. This is about discontinuities and derivatives, okay? That just summarizes something useful. You can use piecewise plot piecewise to plot piecewise functions. Okay. Okay, Zhao, that's a good start. Zhao says fx equals x squared when x is negative, fx equals minus x when x is positive. Let's plot that. Did you say fx equals x squared when x is negative? Fx equals minus x when x is positive. Let's try this. Does that satisfy the condition? Remember, we want x equals 0 to be a local maximum. Can you think of that? This is a good start. Okay, you can play around with other functions like this, but these two doesn't really satisfy the condition. Okay, I'll give you time to think about this, and then let's move on to question 2. Okay. The following graph describes a function f on the interval -2 to 6. List all critical points in the interval -2 to 6. Okay, can you give me all the critical points? Maybe I'll give you 1 or 2 minutes. -2, -1. Yeah, we want all the critical points to be within this like open interval. So -2 is not included. Okay, triplet says -1, -1 plus 1, yeah, 0, -1, yeah, and 1, 0, yeah, okay, so someone says -1 plus 1, yeah, that's a critical point, and 0 -1 is a critical point, and 1, 0, someone says a critical point. Are there any others? 2 -1 is a critical point. Anything else? Just the 0.3 -1? So yeah, that's a good guess. Is that the only point? There are others. Can you think of where the derivative equals 0 or it does not exist? Okay, 5, 1 is a critical point. Why? Throw. It does not exist. That's good. And okay, by the way, at these points, at the corners, does the derivative exist or not? It does not exist. Okay. So at x equals -1, there is a critical point. X equals 0. Okay, at x equals -1. What type of critical point is that? Do you think so? Is it defined? Is the point defined? Can you draw a tangent line at that point? Draw. If you can't draw the tangent line, then it does not exist. Okay. X equals minus 1, 0, yeah. X equals 0. X equals 1. And then someone says 2. 2. And someone said 3 as well. The other one is minus 2. And then someone said X equals 5. Okay, these are the values of X where the critical points are. And at X equals 1, this is there is a jump discontinuity. Discontinuity. Um, 0, 1, 2 are corners. Okay, 5 is, what do you call that point, that type of critical point? At 5, what do you call that type of critical point? It's here, okay? At 5, 1, what do you call? That's a point of, it does not exist. It's a point of inflection, okay? There is a vertical slope, okay, there. And you missed a lot more, okay? There are a lot more critical points. Can you identify which X values? Yeah, Zhao, very good. Okay, in fact, the whole line for X equals 2 to 3, okay, the slope exists, the tangent derivative exists, and because the slope is 0, and so that would be the open interval 2, 3. That's exists. Okay, any question? No questions? This is the interval 2 to 3. Okay, this whole line 2 to 3. Okay. All right, any question regarding that? I hope that's clear. -1, 1. So because this point, there is a hole, it's not defined. The value is down there. Okay, let's move on to, is there any more question regarding number 2? Okay, let's do question 3. Show why the function pt equals, this is called the growth curve, is the only solution to the growth equation p dash equals k times p with p0 equals c. How would you show this? Any ideas? Yep, you can, yes, the derivative is 0. Yep. So that the line at that interval is a critical point. All those points between 2 and 3. Is that clear? All right, question 3, I'll give you a hint. How would you show that PT is the only solution? With C as the constant. Let's say, suppose instead of C, let's say Suppose PT is equal to AT times e per KT. Okay. Can you use this PT to compute P dash and sub into the equation P dash equals KPT? What's the derivative of PT in this case? Could you give me the derivative of PT, this part? No, when you derive PT, what do you get? Remember, PT is AT times e per KT. PT equals okay, this is like a function with respect to t, and that's also a function with respect to t. What sort of rule do you use for this derivative? So, okay. Okay, product rule tracker. Thank you. I think Zah has given us the answer. Okay, let me write. Okay. That's the left-hand side of this equation. And then the right-hand side is KPT. So equated that. We get cos K. Okay, now what do you notice? PT is KT. Now what do you notice? Since e to power KT is always positive, yeah, and then you have AT, we can divide through by e to power KT. Finally, you will have AT equals 0. So what should A be? Yeah, that's a good observation. If the derivative of function is 0, what would be that function? Constant. Good. We can say constant C in this case. Therefore, we arrive PT equals C. Okay, so done. Any questions? No question? All right, let's do the last one. This is about Maclaurin series. I hope you have covered Taylor series and Maclaurin series as well in the lecture. Okay, good. So can you describe me what's the difference between Taylor series and Maclaurin series? Yep. when the function is 0, that's the Maclaurin series. Okay, let me show you my notes. All right, this is the definition of Taylor series. Taylor series of a real or complex valued function f that is infinitely differentiable at a value a, real or complex at a real or complex number a is the power series. Okay, so you would take f at a point or at the given point, then take the first derivative, divide it by 1 factorial, take the difference x minus a, and then goes on. In series notation, this is called the power series. Okay, you can use Mathematica to generate this series. Okay, using the series notation. There is a function called series notation which computes this at a given point. Okay, and Maclaurin series is when the point a is 0. For example, the Maclaurin series for e to the power x is given by the first one is when f of 0. So in this case, your fx is equal to e to the power x. So fx is, the first one is f of a, which is f of 0 plus f dash 0 divided by 1 factorial x minus 0 plus f dash 0 2 factorial x minus 0 squared plus, and then it goes on. So I've computed that these values, and then the expansion, the Taylor's Maclaurin series expansion in compact form is given by x to the power n, sum of x to the power n divided by n factorial, which is commonly used in statistical modeling, and which is a very commonly used expression or series expression. Okay, you might have to use this in one of the questions in the assignment. Okay, any question? Now in this question 4, I've asked you to approximate e to the power x using Maclaurin series. So to approximate this, what you have to do is you say limit is maybe k goes to infinity, take this x to the power n, n factorial, n goes from 1 to k. So you would need to code this. This is like what we did previously in last week. So E for x is approximated by that. Any question? Let's do this. Let me first show you how you can use the series function in Mathematica. let's say you have a general function. Mathematica can recognize it as fx, and then, oops, maybe I need to clear f. Right. But if you want to change the fx to something else, you can still use the exponential form. Okay. That's that's e to the power x up to order 4. Okay. Now, if you want to truncate this and then find just wanted to use just the expression, then you would say normal. Okay, so that's one way you can use compute these terms to get an expression. Okay, but if you want the series notation, you would need to use the sum formula. For example, that's sum of x. No. Okay. Remember, e to the power x can be written as sum of x to the power n divided by n factorial, which is the same as the previous one. If you want to do the up to order 4, you can say that's 4. Okay, which gives us the same expression as when we did the normal. So in my coding, I'm going to use that one. Okay. Let's first create a function. With that. And then let's see if we get f of 4 is the same as what? Yeah, it does work. F of order 5 is that. Okay, now let's build let's plot this with e to the power x. Okay. We can use, remember in week 1, I've taught you how to use manipulate function. I'm going to use that. All right. Or otherwise, if you just want to plot function. This is when k is 10, but if you let's change that to 5. Okay, we don't see that. Maybe 9. Yeah. 12. Why is this going down? Instead of changing this number every time, let's use manipulate function. So the manipulate function is like the video. So it plots the function f of k and the e to power x function, and then gives the legend for, and then every time k is increased, it just changes the curve. Okay, let's say we see by the time it reaches 10, the approximation is almost similar. Maybe we need to change that. All right. Any question? Okay, I think we are almost. Is there any quick question regarding assignment? We are almost time. I can give you 5 more minutes. And whatever I have done in today's track, the coding will be uploaded on GitHub. Okay, please have a look at. Is there any question? Okay, I really need to go because I have another class. Okay, if there is any question, could you please post it on Piazza? Okay. Thanks a lot for attending.